Welcome to the opening of the EE-Just Symposium, where we are making history at Dartmouth College. And I guess Joe Bloomberg, thank you very much. We'll leave it up to our science communication person at Dartmouth, Joe Bloomberg, to explain that to us in the near future. Who am I? My name is Stefan Alexander. I am a professor in the physics department. I'm the EE-Just professor, 1907 EE-Just professor. Thank you. Thank you very much. Oh, please, please. And I'm also the director of the EE-Just program here at Dartmouth. I need to go back here and sort of read certain things. I have a very bad memory. So first of all, this whole event would have been impossible without the help of many people, and I want to just bring some attention to them because to really express my gratitude. First of all, I would like to thank our Dean of Sciences, Professor Dave Coates, the man sitting right there, and the Dean of Sciences, Mike Matsunduno, who is currently in China. He sent me a private phone call to explain, that. Just kidding. The Dean of Faculty, and David Spaulding, the Senior Vice President and Senior Advisor in the Office of the President, for their support of my vision for the EE-Just program and for this symposium. When I was considering the job, I went to Dave and Mike and said, hey guys, would you do the impossible? And immediately they were like, that's a cool idea. And then they went even beyond that. So really, thank you, deans. Financial support from the symposium was provided by the Dean of the Faculty Office and by the Master of Arts in Liberal Studies program. I particularly want to thank Don Pease, Chair of the Master of Arts in Liberal Studies program, and the Ted and Helen Geisel Third Century Professor in the Humanities for his support of this great opportunity for outstanding scholars to engage one another and the Dartmouth communication in exploring the frontiers of interdisciplinary science today, right here at Dartmouth. The symposium wouldn't have been possible, and this is serious, with the incredible support and collaboration of Kathy Weaver and the Office of Undergraduate Advising, in particular the director of UGAR, Margaret Funnell. So could you ladies please stand up and get our appreciation, Margaret and There's a few more. I want to bring attention to two gentlemen who have basically, as we say, they held me down during the course of the planning. The Assistant Dean of Undergraduate Student, Paul Buckley, and Tyler Melancon, Presidential Fellow and recent Dartmouth graduate of class of 2012. Could you gentlemen please stand up and get some love? And last but definitely not least, because I have to live with these people for the rest of my, my life. I definitely want to give thanks to my chairperson and my theoretical headbutton partner and flutist, Miles Blencow, professor and department chair of the physics department, and Judy Lowell, department administrator. Thanks also to conferences and special events, Classroom Technology Services, and the Office of Public Affairs for their behind-the-scenes work to make the symposium happen. Basically, I didn't really do anything, So I just want to spend like a few more, literally less than 5 minutes to just contextualize this symposium and what this whole thing is about, for me at least. It's about somebody that makes me very proud to be a faculty and a member of the Dartmouth community, which is EE-Just, which the person that this college supported in 1907 who graduated from this college, magna cum laude. And to be part of that legacy, a big part of what we do in science is also the human aspect of doing science, which are the relationships that are developed, and also the legacy and values that are passed on. Many of the speakers are not only just collaborators or just famous scientists, but these are people that have passed on values that have made me who I am, have mentored me, and passed on also scientific knowledge. And I would like these speakers to all stand up and just please get our warm appreciation for taking your busy time off your busy schedule to be with us. Please, the speakers. So what are these values? What are these values? Because, you know, since 1907, this legacy lives on here at Dartmouth, and we have this EE-JUST program that is now going to, I think, skyrocket. And I'm going to say a few words about what this program, you know, where it's going, in my opinion, and in our opinion, I hope. But I want to say a few things about EE-JUST. There is actually an EE-JUST scholar, a molecular biologist, who studies the impact of EE-JUST science at Howard University. His name is Malcolm Burns, and I'm just going to read from his research on EE-JUST. It is clear from just writings that, that he believed that life arose out of the complexity and structural integrity of living systems. In his book, The Biology of Cell Surface, and written in 1939, so let's contextualize how we are thinking about complexity theory today, okay? So this is 1939, I quote, he wrote that life is a harmonious communion of events, the resultant of the communion of structures and reaction. Just rejected purely mechanistic explanations. He posited that cells and organisms are, quote unquote, more than the sum of their parts. According to this view, the properties of any level of organization, such as molecules, cell tissue, and the whole organism, depend on the properties of the parts of the level below as well as on the properties of the whole into which they are integrated. Moreover, properties are said to emerge out of the organizational complexity of the living system. What made Just different from his peers was his unflinching willingness to take on giants of biology in his quest. This is, remember, this is the early part of the last century. This is an African-American man who could not get a job in the United States, get a decent faculty job. He did end up working at Howard, but he soon took off to Europe. So he, nonetheless, he was fueled by his conviction, by this conviction, his scientific truth, to challenge the most prominent. For example, at the 1935 American Society of Zoologists meeting in Princeton, New Jersey, David, he publicly challenged Nobel laureate Thomas Hunt Morgan for his gene-centered view of development. Whoa, that's kind of, I would never do that. Morgan had proposed that genes arranged in linear arrays on chromosomes are both the units of inheritance and the controllers of the whole developmental process, the whole phenotype. In opposition, Just presented his own cytoplasm-centered theory of genetic restriction to explain how differentiation occurs during development. Just explanation contains some elements of truth. Indeed, and this is very important, today we are learning that differential gene expression, you can go to Professor George Langford to explain that, or some of the biologists here. But differential gene expression is a multifaceted process with epigenetic as well as genetic components. So in other words, Just played a major role in epigenetics, as I was corrected by Joe Bloomberg weeks ago. That's kind of what led me into this thing. And please spare me for 2 more minutes, and we'll get the keynote speaker, but this is kind of important to me. What made Just different from his peers was his unflinching willingness to take on, I'm repeating my stuff. Okay. But perhaps one of Just's greatest contribution, this is my words, is the legacy of excellence, courage, and passion he displayed as a scientist. Okay. This gift is what inspired the EE-JUST program. So one of the best gifts, I think, is actually the fact that he lives on today through us. This event to celebrate the EE-JUST legacy of scientific courage kicks off the new EE-JUST program. This program is for all Dartmouth students, with a special focus on increasing the number and excellence in science research opportunities and scholarship for underrepresented groups. Important to this end are events like this one, where students are enabled to engage in real-life science symposia, debates, and collaboration with world-class scientists, Dartmouth faculty, and their own peers. At the end of the day, the EE-JUST motto should just be, science is the coolest thing around. So before I begin, I ask our speakers to stand up. Oh, I already did that, sorry. Erase that from the video camera. Now I would like to introduce our first keynote address, because there are going to be 3 keynote addresses, and please come to these talks. They're going to be really cool. I got to stop using that word all the time. People stop believing me. In the spirit of his just legacy, Professor Jim Gates stands as a living example of scientific innovation and courage. As both an undergraduate student and PhD student at MIT, like Just, Jim was faced with challenges, encountered with senior colleagues doubting his desire to pursue theoretical physics. I noticed from my own personal interactions with Jim some 20 years ago. Jim's answer to those doubts was to produce the first PhD dissertation on the new field at the time called supersymmetry. There are fundamentally 2 forms of matter, bosons, which are the force carriers of nature, and fermions, particles like electrons and quarks. Supersymmetry radically relates bosons to fermions, thus uniting two thought to be distinct forms of matter. Professor Gates received his BS and PhD from the Massachusetts Institute of Technology. His doctoral thesis was the first at MIT on supersymmetry, and he wrote the much-feared book, 1001 Lessons in Supersymmetry, with Rocek, Grisser, and Warren Siegel. Well, I can go on and on about Jim, but let me just say that, aside from his role as a physics professor and a physicist, he also serves on President Obama's PCAST, which is Obama's Science and Technology Council. And he's always, you all see Jim on Nova or somewhere on TV. So without further ado, let's give a round of applause for my mentor and colleague, Jim Gates.
Speaking of always being on TV, I have a joke, but we'll get to that in a moment. I'd first of all like to thank all of the organizers of this meeting for allowing me to be part of this celebration. EE-JUST is someone who I can remember maybe 15 or so years ago. I'm sorry, longer than that. I just saw a friend in the back, and 2 friends actually, and I'll embarrass them. They'll be speaking later in the program. But I remember when I first came across reading about EE-JUST, and at a time when I just thought, wow, that's the coolest thing. That guy got out there and did the game the way he wanted to do it and didn't let whatever the organizational structure in science, which is quite subtle, he didn't let it stop him from giving some very individualized views at a time when most people felt that people of the African diaspora had absolutely nothing to say about the sciences. And so he was just, for me, just an inspirational figure to find out there in the country and the legacy that he left. So first of all, I'm very grateful to the organizers for the opportunity to be part of this celebration of this incredible individual. I also wanted to extend a special thanks to Stefan and Kathy, and there are other people in this room, because in the run-up to this meeting, there's always last-minute stuff that has to be done, and so emails are flying back and forth, and everyone was in good cheer and good spirit, and we have brought the program to this point, and I'll try not to drop the ball in this opening address. My joke is now coming. You notice I have to warn you so you'll know that it's actually coming. It turns out that for very strange reasons, which I don't get, I keep having the same set of circumstances occur to me, and I'm going to tell you one of the times this happened. So I was getting on an airplane in Johannesburg to come back to the United States. And as I was walking towards my seat, there was a gentleman. I had a window seat because I like windows because I can go to sleep and I don't have to worry about people waking me up. And I love to sleep on airplanes, by the way. Turbines, to me, are like lullabies. They literally sing me to sleep. I can sleep on an airplane anytime. Going to Australia is a bit of a challenge, but short of 10 hours, I don't care. I can sleep my way there and sleep my way back. So I was trying to make my way to this window seat on this occasion, and this gentleman saw me approaching, and he looked up and he smiled, this brilliant smile. And he said, "Is this your seat?" with a slight Afrikaans accent. And I said, "Yes, that's mine." He said, "Here, let me move out of the way." So he jumped up, and I had some bags to put up on the overhead, and he was helpful with me getting the bags up. And I thought, God. Now, this was not my first visit in South Africa, but I thought this is one of the most helpful, friendly South Africans I've ever met. And so I get situated in my seat, and I'm sitting there, and I had a book that I was starting to read, and so I'm looking down at my book, and on the corner of my eyes, I can see him looking over at me, and he's got this big smile on his face. And I'm thinking, there's something not quite right about this guy. So it's better to confront him now and find out what the issue is than to stay on the plane for some 8 hours wondering what's driving this behavior. So I turn and speak to him, and I say, "Goeiemiddag." I don't know if any of you speak Afrikaans, but that's basically good day. I speak a little bit of a lot of languages. It surprised him, and he responded. And then he said, "So, going back to the US?" And I thought, yeah. I said, "Yeah, I've been here in South Africa 2 weeks on this journey, and I've had a wonderful time in the Western Cape." And by the way, if you haven't been to the Western Cape, it is one of the most spectacular places in the world. Go to the Western Cape. It's just an incredible place. And so he said, "Going back to the US?" I said, "Yes." And he said, "Did you enjoy your stay here?" And I said, "Well, yes, this is not my first time. This is probably the 8th or 9th time I've been to South Africa." And then he said, "Well, I'm happy to hear that you had a good time here." And I said, "Well, thank you." And then I went back to reading, and again, I turned my head, he's still smiling broadly. And so finally I said, "So is something going on?" And he said, "Well, we've all seen you in the media." And I thought, gee, I didn't know that Nova had such a large impact with scientific documentaries around the world. Because as Stefan mentioned, I've actually appeared on Nova, I don't know how many times now. And so I said, "Oh, are you a fan of science?" He said, "No." And so at this point, I'm like, "Well, where did you actually see me?" He said, "Oh, come on. All of us have seen Invictus." And then I had a hard time convincing him that I am not Morgan Freeman. Now, the strange thing about this story is, A, that it's true, but B, there are at least 7 or 8 different variations of this story that have happened in places like Singapore, Vienna, Australia, and even here in the United States. And I don't know where people get this from. I don't think I look like Morgan Freeman. And yet, if some of you are fans of TV science documentaries, you may have heard of this thing Through the Wormhole. Who's the host of that? Morgan Freeman, right? So I'm always telling people, no, I'm not Morgan Freeman. That's one of my standard lines is, I'm not Morgan Freeman. That was the end of my joke. So let's try to get on to some more serious business. The title of my talk is Susie and the Lords of the Ring. And someone was asking me, well, gee, what does the Lords of the Rings have to do with physics? And that's what I'm going to try to tell you about in this story. So in 1975, I was a graduate student, as Stefan mentioned, and I was trying to figure out how I could realize my dream of becoming a theoretical physicist. And in this quest, I stumbled upon this fantastic idea. And I read about this thing called supersymmetry, and it suggested that there were more forms of matter and energy than anyone had ever thought about before. And I was just stunned, because who gets to be alive at such a time when such an idea is actually bubbling up out of the field? I mean, how incredibly lucky can one be to have come into a field just as this idea comes into blossom? And so I started running around the department like someone with their head on fire, trying to get other people interested in this idea. And very quickly I discovered there was no one else in the physics department at MIT who had any interest in this idea called supersymmetry. Now, up until that point, I had been working with a thesis advisor, and he had been letting me do more conventional physics, but he had kind of gotten the idea that I was okay. I wasn't going to get myself into too much trouble. And so one day I went to him. He's a gentleman by the name of Professor James Young. And I went to him and said, Jim, I've done these research problems that you've given me, but I would like to strike out in a different direction. And he said, well, what's wrong with these problems? I said, well, the problems that I'm working on with you are problems that are, yes, they're in the center of the field. There are large numbers of people working on these problems. But for me, as a young person trying to work on these problems that I knew that faculty members 20 years older than I have were working on, that didn't look like a fair competition to me. And so I said, if I'm going to build a career, then one thing I've got to do is distinguish myself. And one way to do that is to strike out in a direction that does not have this herd of people following that direction. And in fact, my choice of supersymmetry was no accident. I had actually spent about 6 weeks making huge lists of subjects, of looking at all of the strands of thought that a student could look at that were going on in my discipline. And the reason I found this one particular subject was because it had come up on my canvas of what was going on in theoretical physics. And so I said, I want to do this. He said, well, I don't know anything about it. Then he stopped and he said, wait a minute. Nobody in this department knows anything about this. How are you going to do a thesis? And I said, well, I can read the literature and I can understand the calculations that people are doing, and I think I know how to get to where the questions are in the field. And so he said, okay, I'll let you do this under one circumstance. Every week on Friday, you have to come to my office and give me a seminar on what you've done that week. And so that's how I actually produced my thesis. I had a weekly session with my advisor where I had to present to him where I was in my progress in understanding the field. And so he let me do this thesis. Now, there was a result of this thesis very interesting. So I presented this thesis, and there were 3 faculty members on my defense committee, with him being the head of the committee, which is the norm, as many of us faculty members know, 3 to 5 people on a committee. And so I gave my thesis defense, and boy, it just went swimmingly. It was just so beautiful. No problems at all. Questions came up, and I just batted them away, And the truth of the matter was that I knew more than anybody in the room about what I was doing, because it was a new subject. And so I passed my thesis defense, and one of the people on my defense committee was a physicist by the name of Ernie Moniz, who's still at MIT to this day. And he said, that's the best PhD thesis defense I've ever seen. And as I was walking out of the room, I was thinking, ha, 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 you don't know what I just did. Because, see, I'm a Star Trek fan. And I don't know if I say the expression Kobayashi Maru. I got a sufficient number of laughs that people understand the joke. For those of you who are not Star Trek fans, let me explain it. So the first starship captain that the Star Trek quest is about is a guy named James Tiberius Kirk. And Kirk is a graduate of Starfleet Academy. And in order to graduate from Starfleet Academy, there is a computer simulation that is given to all potential captains. And the computer simulation is basically you're in your starship defending it against some attacking forces. And you have to figure out the best strategy to save your starship. Now, what they don't tell the students is that no one passes this test because the code is written in such a way that you can't. No matter what decision you make, you're wrong. So in the entire history of Starfleet Academy, there's only one person who passed the test. His name is James Tiberius Kirk, and the way that he did it is the night before the test, he rewrote some code. That's what I did for my thesis defense. Because I rewrote the code of what we would be, I changed the terrain, the intellectual terrain in which we would be having the discussion. And like I said, it was just trivial. So that's how I got my PhD and wound up going to Harvard and Caltech. And so anyhow, I got excited about this idea almost 40 years ago now. And pretty soon we're going to find out whether nature herself is excited about this idea. And that's what this talk is about. So let me try to get you there. So we're going to be trying, because of time constraints, I'm going to be rushing a little bit. So if people want to ask questions afterwards, I'll try to save time for that. You know, if you walk into almost any high school classroom on science, you'll see this thing. It's the table of elements. I like to think of this as the Mona Lisa of science, because it's a little bit mysterious, but very familiar to even people who are not scientists. They've seen this thing, just like the Mona Lisa painting. And it's, of course, given to us by Mendeleev. And one of the interesting things about Mendeleev's presentation of this is, probably many of you have heard of Sergey Brin. Sergey's father is a mathematician who had a career. He's retired now, but he spent his career at the University of Maryland. So I was actually with the elder Brin one day, and we were talking. And he said, Jim, you know the Tsar gave Mendeleev a medal for his work. And I thought, oh my God, a Tsar that is so forward-looking that he would give a scientist a medal for the creation of the table of elements? And he said, no. The medal was for the improvement in the distillation of vodka. For my generation, this is the equivalent of the Mendeleev table. It's something you'll find in many physics departments, and it tells us what are the basic parts that you need to put together our universe, and it comes to us over about a course of a century. The oldest part of this is the electron, and the electron is in fact the first elementary particle. It was proposed by an electrochemist named J.G. Stoney back in the end of the 1800s. And he was the first person who had the idea that there could be something in nature that was smaller than an atom. He actually named this thing, and then about a decade after naming it, it was actually discovered in the laboratory by J.J. Thomson. But the electron is the first elementary particle. So ever since the work of Stoney, we've been discovering more and more of these objects. So there's an object in nature that always looks like an electron, except that it's 200 times as heavy. We call it the muon particle. There's another object in nature that has all the properties of the electron, except that it is 1,700 times as heavy. We call it the tau particle. And then there are a set of objects that have many of the properties of the electron, but they have no charge. We call them neutrinos. So this is part of how you put together our universe from 100 years worth of science. Our country spends about $750 million a year to get this kind of science. We do it through the support of principally through the Department of Energy and the National Science Foundation. But that's how we know these things about nature. Inside of nuclear matter, there are things called quarks. We're going to come to those shortly. And then all of these particles have to be held together in fixed patterns. Otherwise, when I look out at you, you would just be a soup of particles as opposed to this very beautiful image that you present to me as you sit there. So these fixed patterns have forces that cause them to be held in place, and the forces themselves have particles which carry them. The particle of light, the photon, is to carry the electromagnetic force. In nature, there are two forms of nuclear energy. There's strong nuclear force and the weak nuclear force. The weak nuclear force has three carriers. They're called the W and Z bosons. The W and Z bosons come in positive and negative varieties. The Z is neutral. And then finally, there are 8 objects which are the glue for nuclear matter. Let's talk about that for a moment. This is what a proton looks like, sort of. Now, normally when you say protons, people think little balls, because that's what most of us learn in science, but you really should think about them as bubbles with something inside of them. These things inside of them are the quarks. The proton itself is actually the bubble structure that I've represented here in an allegorical way in this image. And it's not a static place. In fact, it's very dynamic. The quarks inside move around, and if I ignore quantum mechanics, I don't have to worry about particle creation, but it turns out that if you try to pull a quark outside of a piece of nuclear matter, you never get it out. If you looked at the image that just happened, what you see is I pulled one quark out, and this piece of bubble split into two, but a second quark was actually created to accompany the first. And the reason is because as you pull the bubble, it's like pulling on a rubber band. When you pull a rubber band, you put energy into the rubber band. And Einstein says energy and mass are the same thing. And so this energy that you pull and stretching the nuclear matter turns itself into more matter and then splits off, and you don't have a free quark, but you have a quark bound inside of another piece of nuclear matter. Quarks are numerous. So the proton and neutron quarks are what make up protons and neutrons, but there are lots of other quarks. Quarks have a property that we call color. Now this is one reason you can tell that theoretical physicists are, so we say, tilted. Because if theoretical physicists were as rational as chemists, instead of calling this color, we would say something like electronegativity, because that's what chemists call a, roughly speaking, analogous property that governs the behavior of molecules. The proton has a mass of 338 MeV in a certain set of scales. It actually spins like a little basketball, and it spins at a rate of 1/2 h-bar. Similarly, the neutron is slightly heavier. The electron is actually the lightweight in the atom. It's about 1,800 times less in mass than the proton. And, all of them spin. So what is spin? Well, we're going to come to that. These things act like little basketballs. You know how the Harlem Globetrotters used to go out and take a basketball and set it spinning? Well, these objects have the same behavior with the exception that you cannot speed them up nor slow them down. So it's like having a basketball on your finger that just spins at the same rate and you can't do anything to stop it. Electrons have that behavior. This was discovered in the 1930s in a famous set of experiments called the Stern-Gerlach experiments. Now, not everything spins at the same rate, however. All electrons spin at the same rate. All quarks spin at the same rate. But the force carriers spin at twice the rate of the electron. Antimatter is real, folks. Again, for all of you Star Trek fans out there, you know that the engines of the Starship Enterprise derive their ability to transcend the speed of light by matter-antimatter reactions. So you might think antimatter came from a science fiction writer. But the truth of the matter is that the idea of antimatter started with a scientist, in particular with Dirac, who wrote an equation. He wrote the equation trying to describe an electron consistent with Einstein's laws of special relativity. He was the first person to try it. He succeeded in finding such an equation. He looked at the solutions. One of the solutions described the electron exactly like he set out to do, but he found there was a second solution. This second solution had all the properties of the electron except it had the opposite charge. More interestingly, if you brought these two solutions to the same place, they would disappear, and in their place would be a puff of energy that satisfies precisely the famous equation E equals mc squared. So that's what antimatter is. It's a real thing. It was discovered by a scientist quite by simply looking at some mathematics. And this brings us to the power of mathematics. Many people don't understand what mathematics does for science. It turns out that for the scientists, mathematics is an extrasensory perception organ. It is. I don't understand why that's a joke. Oh, the mathematicians are over there. It turns out that mathematics, in addition to being what I like to think of as the incomparable human language, because there is no other human language like mathematics that we have ever created, but in addition to these special properties, it is the only way of organizing human thoughts that we have ever encountered that allow people to model the universe, that is to think about the way things are in the universe in such an accurate way that it allows us to see things that we cannot see with our instrumentation, that we cannot feel with our fingers or any of our senses, and yet mathematics allows us to do this seeing. It's an incredible thing. In fact, I'm not the first person to notice this. There's a very famous quote by Charles Darwin who said, with mathematics, it is as if an individual is endowed with a new sense. And that's the sense in which I use the word extrasensory perception organ. I have my 5 normal senses for perceiving the universe, But because I can use mathematics in this very peculiar way, I'm also able to perceive the universe with that as a sensory organ. One final story about the power of math to sense the universe. I'm a professor, so I'm going to give a pop quiz. How big is an atom? Well, there are a lot of scientists in this room, so you know the answer. So you guys are excluded from this question. For those of you who are not scientists, let me give you a story to remember the answer. If I take a yardstick and cut it into 10 equal pieces and throw away 9 and keep 1, I go from something this big to about something that big. Let me take that piece, cut it into 10 equal pieces, throw away 9, keep 1. I get down to something about the width of my fingernail. So that's just doing this process twice. How many times do I have to do this process to get from our world to the size of the atom? Now, when you ask people, and I'm not going to put you non-scientists on this spot, we're not taking tally, and we're not going to collect your test results. But when you ask people in our society this question, almost no one who is not a scientist knows the answer to this question, which is quite remarkable because everybody has heard of atoms. But almost no one knows how big an atom is. To me, this is a stunning situation. And so this story that I just told you is a way to remember how big an atom is. You do that process, which is called powers of 10. You do it 10 times, you get to the size of the atom. Who was the first person to know how big an atom was, or is? Again, not many people know. But it turns out it's a guy named Albert Einstein. Now, you've heard of him because he's done lots of stuff, and David is involved in some of the stuff that he's done, and there are other people like Stefan. But you don't know that he was the first person to figure out how big an atom was. And he did it in the same year that he worked in his theory of space and time and relativity. That same year, he wrote a paper on Brownian motion. And in that paper, you have to know the size of an atom. And in fact, he was able to figure out how big an atom was from that work. So Einstein's the first person to know how big an atom is. And that's why he's the first person to see an atom. And that's what I mean by mathematics is an extrasensory perception organ. So antimatter is real. Let's keep trying to go ahead. There are forces in our world. Now, Stefan, how good are you at catching things?
I used to be.
We're going to try this experiment time, folks. Okay, so he caught my phone. Now, imagine that I did that. No. But actually, yes, because it's so old. No. Now, so imagine that I did that 100,000 times, that same thing that you just saw, over and over and over again. And I did it not just 100,000 times, but I did it in exactly the same way, where I released the ball at the same point, with the same angle, with the same speed as it leaves my hand, 100,000 times. And you had a video camera and you were filming that. What would you see if you did that? And let's imagine that on the last time that I did it, your battery died. So you could only catch me tossing it, you put a new battery in, and then you catch the image of Stefan catching it. And then I ask you, what happened when your camera wasn't working? Well, if you went back and reviewed all the 999,999 times, you would see it was exactly the same picture. And so you would be confident that even though your camera wasn't working on that one last time, you would say, well, gee, it had to do the same thing, and you would be right. Let's change the story. Suppose I did this with an electron. Thought experiment. So I do it with an electron, same number of times, same circumstance, and the last time your battery dies. And so I ask you, what happened to the electron while your camera wasn't working? Now, it turns out that if you reviewed all the previous films, it might be the case that every single one of them looked alike. It might be the case. And so you would probably, on the basis of that, say, well, same thing happened, because that's what happened with the baseball or my phone. And if you said that, you would be wrong. Because it turns out that for an electron, if we could manage this thought experiment, I might release the electron. It might leave my hand, circle around George's head 137 times, come and circle around Kathy's head 137 times, and then go to Stefan's hand. Now, that sounds like something out of Wile E. Coyote and the Roadrunner, right? You've never seen objects behave that way. But it turns out electrons behave like that. That's what quantum mechanics is about. The world of very small is not like the world that we see around us. And in fact, we need very different mathematics to describe the motion of these tiny things. And that's what quantum theory is all about. So the classical path can be thought about as straight lines. Oh my goodness. Is the text here because I'm having an issue with power? I just got a warning that I'm running out of power. Now, this is not the first time this has happened to me, folks. Once many years ago, I have a battery here. Once many years ago, we got light, we have power. Yeah, let's try this. Once many years ago, I was giving a talk at a conference in front of about 1,700 people, and this same thing happened. I had a presentation where the system just died. And it turned out that although I was plugged into the power strip on the floor, no one had plugged that power strip into the wall. So you learn all kinds of things when you speak to people. And we're not sure what's going on here, but we have a solution. So the quantum path can be thought of as a regular thing that happens when electrons move. And we can compare the two. They're very different. The mathematics that you need for them is very different. And in fact, the mathematics is so strange. Let me do this. Classically, if you watch a ball roll down, it's again like the tossing. This time I put a little ball at the edge of a bowl and put it in the same place, same way every time. It always does the same thing. But in a quantum mechanical universe, this can happen. The ball may suddenly be replaced by more than one ball. The ball may wander around the sides of the bowl. This is what we mean by quantum weirdness. And the equations that we write in quantum mechanics actually tell us that electrons do this stuff. That's why quantum mechanics is so very weird. Okay, thank you. So it affects the forces. It turns out that in our universe, forces are actually transmitted by force carriers. So two electrons are repelled from each other. If I can get my technology to work with me, there we go. By exchanging a force carrier, which says one should move away from the other. That force carrier is the electron. And that's a little bit like our classical ball just rolling down one by one. But if we go to a quantum mechanical universe, weirdness intrudes. So let's get to some of the weirdness. In the quantum mechanical universe, extra things that were not part of the story before can occur. This is one such thing. This is what we call vertex normalization in quantum theory. And what it basically says is that the charge that an electron couples to a photon with actually depends on things such as the speed and the spin and the location, much more complicated than the equation we taught our students in high school. You see, we constantly lie when we teach science. But we lie in the service of truth. We tell people the part of the truth that is appropriate for what they have as a background. It would make no sense for me to walk into a high school classroom and try to teach my students relativistic quantum field theory. And so instead I say, Coulomb's law is the end of the story, even though I know that is not the complete accurate story. But it's good enough for that audience. So when you talk to a scientist, you need to be very careful if you're not a scientist, because you need to know what the scientist is assuming about what you know, because that influences what we will tell you. Here's another process. This is called the vacuum polarization. And this one, a photon is emitted. It splits into a particle-antiparticle pair, which later annihilate. And then this second photon is the force carrier. And it leads to something other than what Coulomb's law tells you. And there are hundreds of these diagrams that you can write. They're called Feynman diagrams. That's why Richard Feynman was A, genius, because he's the first person to figure this out, and B, won a Nobel Prize because he did it. Notice that even though you're not trained as a relativistic field theorists, it's a pretty simple story. There are these pictures, you use them to calculate the forces, and then you draw fancier and fancier pictures. That's the net upshot. Won a Nobel Prize for one guy. Now, how real is this stuff? Well, I like to tell people, I don't have my phone on me, but I like to tell people that this is the most accurate part of science in terms of theory compared to experiment of any science that there is. It turns out by these pictures we can figure out that the electron is like a little magnet. You can ask, how strong is this magnet? These pictures are the answer to the story. And if you just draw one picture, the simple picture, the simplest possible picture, you'll get the answer 2, is how strong it is as a magnet. But when you start adding these extra pictures in, you find out that the strength of the electron actually changes. So it gets a little bit bigger and bigger and bigger. And so this number here is the measurement of how an electron behaves like a magnet. The number at the bottom here is the picture-making mathematical machinery that predicts how strong it is as a magnet. And if you look at these two numbers, what you see is that they agree until you get to the last 2 digits. This is the most accurate thing we know in science. So when people start to question quantum mechanics, the questions that you're raising are not consistent with what we see in the laboratory. So quantum mechanics is very well founded in terms of the physical observations that it relies on. Let me, because I don't want to bore you folks, let me just jump ahead here. So I'm going to go now to the ring part of my story. So that first part, you didn't see Frodo in there anywhere. So now we're going to try to get to Frodo and his friends. The ring. So what ring am I talking about? Well, the ring I'm talking about is the Large Hadron Collider. It is a ring-shaped device that we're going to see in a moment. It is in Geneva, Switzerland. It crosses the border with France. It is a proton-proton synchrotron, which is a fancy way of saying that we take protons and bang them together with lots and lots of energy. In fact, the energy is described by this 7 TeV per beam. The size of this ring is 27 kilometers, which is about half the size of the beltway around Washington, D.C., for those of you who know about the beltway, you know, inside the beltway, outside the beltway. And it is a real device that has been in operation. If you flew over Geneva, you'd see this. Well, actually, I told you I was going to lie, so I just told you a lie. You would not see the red ring. You would see everything else. The red ring is a superposition of what is under the ground, where the ring sits, because the ring is actually underground. In this image, you can see Lake Geneva over here to the side, and the Alps up in the background. And the city of Geneva, of course, is sitting here. So 16.8 miles around. As I said, it crosses the border between France and Switzerland. It is underground. It is, some places it's 75 feet underground, and other places it's about 150 feet underground. And you might say, well, that means the ring is tilted. Well, no, the ring is even. The ground is tilted because it's tilting up towards the Alps. In the ring, we put large devices. So this is actually, if you went to Geneva and you went down to the experimental ring, this is what you see. It looks like a big petroleum pipe. So the world's most advanced science is being done with petroleum science, right? But inside of this pipe, we evacuate the air. We pump the air out, and then that's where we let the protons move. And we want the air out of there because we don't want them bumping into air molecules. So you got to pump the air out. Another view. There are 2 detectors that we in the United States have been responsible for building. We've spent about $700 million doing this. One of them is called the Compact Muon Solenoid, or CMS detector. The other is called the Atlas Detector. And this one's a real stretch. It stands for a toroidal LHC apparatus. So you can see whoever was trying to name this thing really went for a stretch because they wanted a nice name. And they strung together words and they picked the letters out to get the nice word. This is a cartoon drawing of the CMS detector. In this, there is a cartoon person, and this is the scale. Here's another view of the cartoon person with the fully assembled CMS. And here is the CMS while it was being constructed. There's a technician here with a white lab coat and black pants in the middle of this. If any of you saw that movie Angels and Demons, remember that big scientific device? That was modeled on this. But the real device is actually more impressive than what they had in the movies in many ways. The Atlas detector, similar, we can see a nice couple here, a cartoon couple standing, to scale in the device. Another image, and the actual device with our technician who has changed clothes. He has a nice pair of brown pants, a black vest, and a hard hat on. That's the Atlas detector. So what these things do is, like I said, speed up protons. So we have a pre-injection device where we start the protons to moving, and then we use magnets to bend them into a circular path, and while they're in this pre-injection phase, we speed them up to their 0.9999999, the speed of light. The fastest humans have ever made anything move. Now, as we watch the operation, after they leave this pre-injection phase, they go into the evacuated petroleum pipe that I showed you, and we let them go around and around using magnets to bend them. And so they pass in bunches. Now, I only have 5 or 6 in this cartoon, but there are like 10 to the 17 or 10 to the 18 of these things rushing past at the same time. And then we allow them, the two beams going in different directions, to collide. And here's a picture of the CMS detector, a cartoon, and a collision where we let the protons bang into each other. And when they do, spectacular things happen. If you notice at the end of that, there was some kind of funny glowing thing. This is an allegory that I've told you. You know, it's not the way it actually looks. I'll show you some computer simulations later of what it actually looks like. But it catches the spirit of what is going on at the LHC. That's what physicists are doing at the ring. This is what a computer simulation of an actual collision looks like. It's a spray of things coming out. A different simulation here, and this particular simulation is associated with something that happened quite recently, and we'll come back to that shortly. Another picture, another picture. So that's what the actual data looks like. It's not these flashing lights and lightning and all this stuff. It just looks like this. A lot more boring. But the spirit is what I showed you before. So something happened this past 4th of July at the LHC, which was stunning for people like me. And I like to call it Born on the 4th of July. Not the Tom Cruise movie, by the way. We talked about earlier the particles. Because of what happened on the 4th of July, we now know that we have to add something new that was not there before. We think it's the Higgs boson, which is a particle we're going to describe. What is the Higgs boson, why it's important, what does it do? But we think we have found a new one of these objects for the first time in over a decade. So it was born on the 4th of July. What happened is that the two devices I showed you, CMS and Atlas, both run independently of each other. And part of the reason we do that is because we know that we like to lie. And so it's hard to get two people to correlate their lies. So if you have two independent groups doing the same thing, you decrease drastically the chance that they both will be convinced of something that's not accurate description. And that's why we have the two direct detectors. The technologies of them are actually different. So we use coincidence and lots of other things in order to make sure that we're not being influenced by what we think we're going to find. Both of them report, however, that they see something at 125 GeV over c squared. GeV is a measure of energy. Now, the Higgs boson, what is it? Well, the Higgs boson, we believe, is a kind of one way to think of it, it's a kind of a molasses that is everywhere in the universe. And what it does is cause other things to become massive. So without the Higgs boson, we think the electron would have no mass. We think the quarks would have no mass. We would think nothing has any mass. And for this reason, this particle has been called the God particle. Except that those of us who know the person who named this understand the real story. If you read the popular press, there's all this talk about the God particle. But the person who gave it that name was really a guy named Leon Lederman. And if you know Leon Lederman, you know he's a rather salty tongue. And so what he really said was, why can't we find the God blank particle? Which was shortened for family-friendly phrasing into the God particle. So if you read in the popular press about the God particle, that's the story behind it. So, as I said, it's a kind of molasses. We'll see that in this cartoon. Here's an ordinary particle moving through the Higgs, which I'm representing by these sheets. And as you can see, it's sort of accumulating mass as it moves along. This is the allegory that goes on with the mathematics. But it turns out the Higgs boson is also responsible for some of the force carriers getting mass. Because I showed you that there were these force carriers. It turns out the photon has no mass, but the WZ bosons do have mass. And so it turns out that the way that they get the mass is not quite by the Higgs boson, but by something called a Goldstone particle, or Goldstone boson. It turns out when you write the mathematics for the Higgs particle, you get this other thing for free. You can't stop it from occurring. Or say it another way, if you write the mathematics for the Goldstone boson, you get the Higgs particle for free. You can't avoid it in the mathematics. It's kind of like Dirac looking for a solution for the electron and then finding this other thing, the anti-electron. Same kind of thing going on, where the power of mathematics is guiding us to see something in the universe we had no idea was there. And what the Higgs boson does, the Boson boson does, is it rolls down an energy surface and it causes the force carriers to gain mass. And that's what I've showed you as a cartoon at the bottom of this image. So the Higgs boson is detected by what we call the decay modes. Remember the actual computer simulations where I showed you all these lines flying out and shooting out in all directions? So what we do is actually detect these lines, and we look back to see if the mathematics of the flying, splashing lines agrees with the mathematical predictions of these things. I have 5 minutes, so let me begin to wrap up. I told you about SUSY. So let me get to SUSY. If you look at that table of particles that I showed you several times, you can group it like this. It turns out everything to the left of this spins at the same rate of a half h-bar. The things to the right actually some spin at twice the rate of the electron. So the W, the Z spin at twice the rate of the electron. The graviton, which is something we haven't seen, spins at 4 times the rate of the electron. And the Higgs particle, the thing that we think we just saw, doesn't spin at all. But the point is that these things are all even integers of a half. So it's either 0, 2, or 4. These things are just precisely 1/2. It turns out in nature, these objects behave very differently from those. But if you look at this table with an artist's eye, you say, that's not very balanced. What would a balanced table look like? It looks like that. It looks like that. That's balance. That's what we humans respond to when we say symmetry, something that looks like that. Now, it turns out that these things that you see to the right, we've never seen in the laboratory. They are the things that excited me when I was a graduate student. Those are the things that the mathematics said new forms of matter and energy existed. They're the things that add to a symmetry in this picture, and we call this supersymmetry. And so I was excited by the possibility that these things existed. Let me tell you about my favorite one of these objects. So this is a quark, that's a squark. That's an electron, that's a selectron, that thing there. This is the gluon, that's a gluino. That's a photon, that's a photino. This is a Z particle, this is a xeno. This is a W particle, and this is my favorite superpartner. Its name is spelled W-I-N-O. So one day, I am hopeful, before I pass off this mortal coil, that there'll be a headline in the paper saying, W-I-N-O seen in Geneva. Now, if that should occur, I want you to know that it will not be an alcoholic specialist that they have found, but instead, this particular elementary particle. So let me begin to wrap up. So this is what supersymmetry is about, looking for these things that we've never seen before, that we think are there. And if nature is kind to us, our mathematics will have predicted these objects that people like me, in terms of the mathematics, have been seeing for roughly 40 years. So I've been waiting in my life to have my bucket list actually fulfilled. And the first item on my bucket list, the Higgs boson, may have actually been fulfilled this past July. I want to see waves of gravity, and that's something that I think David would like to see also, and Stefan. We have other things that before we stop being scientists, and Marcelo also, there are lots of people in this room who would love to see the evidence that the wave-like behavior of gravity predicted by Einstein's equations is something we can see in the laboratory. That's another item on my bucket list of theorists. The other item, there's one other item, superpartners. Those things I showed you, I do sincerely want the CERN laboratory to find evidence of superpartners. Now, it may not be easy. In fact, about 5 years ago, I wrote an article about how hard it might be. It might be a decade or more before we can find these things. But I sure hope that they're there. There's one more item on this list that I didn't put there, and that's a complete theory of strings. But that one is so far beyond anything imaginable, I didn't put it there. I didn't have the courage. So that's where we find ourselves these days. We're perhaps on the verge of actually seeing parts of the universe that we have not seen before. And for me, as I said, this is part of a personal adventure. Let me end by talking about my title, because we still haven't seen Frodo and his friends. So who are the Lords of the Ring? The Lords of the Rings are the scientists who conceive the ring, who operate the ring, the engineers who built the ring and operate the ring. They're the people who actually make the ring bring us scientists. And some of them, by the way, are female. So the Lords of the Ring are the people who have enabled this device to shine this spotlight on what as yet and resides in my heart of hearts as a dream, but may indeed be a story of science I hope to see fulfilled in my lifetime. Thank you.
A few quick announcements. I know that some people, in particular related to admissions, have to leave early. But for those of you that have to go, let's not hold you back. Feel free. And let's get some questions for our Jim.
And while you were talking, I was running some acknowledgments, because this work that I've done in my career is not work that I've done by myself. I have a list of collaborators a mile long, and I wanted to acknowledge them. Their names were given. I'll be happy to give them out. And the graphics, many of the graphics that I used in this talk can be found in a commercial project called Superstring Theory, the DNA, which I created for a company called The Teaching Company. They allow me to use this to make these kinds of presentations, but in return for that, I have to acknowledge that they're actually their stuff.
Questions, please. Yes, Lee? Hi, Lee.
Hi,
Hey,
I'm
Lee.
a bad guy.
Always.
The IC isn't operating for a while, and there are no super partners. We've excluded the deal of the parameter space for them. Are you nervous?
No, I'm not. So Lee's
Why
question
not?
is, so the super collider has been operating for at least 2 years now, and a large part of the parameter space. So let's talk about the parameter space. When you use mathematics to talk about nature, often you have to put in numbers that we call parameters in order to fit the experiment, make the mathematics fit to the experimental results. The mass of the electron is one of these parameters. There are other things like the amount of charge on the electron. And it turns out that in supersymmetrical models, the numbers of parameters are actually in a range of 100. So if you're going to try to use this mathematics to make predictions, the first thing that if you're going to try to make real predictions, the first thing you're going to do is make some assumptions about what the parameters are. Whatever your aesthetics are, you're going to say, it's probably close to this. Let me take that as a guess, and then generate the physics that comes from that. The regions of parameter space that Lee has talked about are those that have been chosen traditionally to be the most likely. But it's only a matter of aesthetics that has picked that. There's no particular other reason. And so that's why people like me are not nervous, because some of us never agree with the aesthetics that were driving those choices.
Okay, good question. Marcelo, let's wait. Since this is being recorded, we'll wait till the mic gets you so that your question is recorded. So. And again, for those of you that have to go, feel free to leave.
So Jim, so the follow-up question is, let's say, in a very pessimistic way, the LHC does not find supersymmetry.
Yes.
Would you be willing to rethink your dream?
Would I be really? Absolutely. Because in science, no matter how dearly one holds a dream, you don't deny the data.
So would you not be willing to tweak the parameters so the
Not
supersymmetry would be
me.
hidden?
No, not me.
Okay.
I know lots of people who would, but the way I'm a very conservative scientist, and I don't believe that you should go running from the data. If the data says something, that's where you ought to be looking. So if we don't see supersymmetry in about a decade, because as I said, I actually wrote a paper about how hard it might actually be to find supersymmetry. I know how hard it might be. If we don't find it in about a decade, then I'm going to get nervous, but not right now.
Okay.
Not right now.
No more questions? Yes, sir. Hillcock.
Oh, there you are.
I'm sorry, I apologize to this young lady who has to run the microphone up and down the hall like this.
That's Ryan Hillcock, one of the colleagues in our physics department.
Hi, I'm just curious. So let's say we do find a supersymmetric particle in the next decade. Which one do you think is the most likely to be found? And why?
This brings me back to, I was hoping someone asked that question, because this brings me back to something that Stefan alluded to in his introduction, or at least talking to the students earlier today. It turns out that among that list of objects, let me pull it up first. So let's get out of this and come back. Come back here. That's exactly where I want to come back to. So it turns out that although I explained in my cartoon explanation of supersymmetry, it was I could draw all the standard particles in a table, and that table was asymmetrical. And so in order to balance that table, I do things that we've never seen before in the laboratory. It's a little bit more complicated than that. And in particular, in the Higgs sector of the theory, it turns out that the Higgs particle doesn't just have a single superpartner, it actually has more, actually has the list of Higgs particles that I've listed here, because I kind of figured someone would come back to this point. And so my favorite of the superparticles is something that is called the LSP, which is the lightest supersymmetric particle. And it is believed that it will be something that's kind of Higgs-like in some sense. And the great thing about supersymmetry, which is one of the reasons why people like me tend to believe it, you see, when supersymmetry was first written, no one was seriously, or at least no particle physicist, was seriously concerned about the dark matter problem. Dark matter, the issue had been raised as far back in the 30s, which Fritz Zwicky at Caltech, as one of the earliest people who pointed out that if you look at the way stars move in our galaxy, they behave as if there's a lot more matter than you can see by counting the stars. And that's how the dark matter issue first came to light in science. Back when I was a graduate student in the early 70s, that problem was essentially not very well addressed except by some people like Margaret Geller, but very few scientists worried about the dark matter problem. As someone mentioned today, I guess it was Robert in talking to the students, he mentioned that if you look at our universe and account for all the energy, we, and stuff like us, account for roughly 5% of what we are able to measure. Dark matter roughly accounts for about another 20%. And then the remaining 75% of the universe is something that is so bizarre and so mysterious that we have essentially no idea what it is, and we call it dark energy. We're like, in this, I must admit that in this way, physicists act like medical doctors. My wife is a medical doctor. And when she was in med school, we were married when she was going through med school. And so I remember helping her study for exams and all that kind of stuff. And while I was doing that, I learned what an idiopathic diagnosis means. Now, some people are here grinning because they know what the joke is. When a doctor's... So for those of you who don't know, if you go to a doctor and try to get the doctor to diagnose some condition, and the doctor says, well, it's idiopathic. Now, you might think that the doctor has identified a cause, but what that actually means is, I don't know. They don't know the cause. And in this sense, when we say dark matter, we're acting like medical doctors. We don't know what that stuff is, but we're going to give it a name anyway. So my point, however, was supersymmetry, when it was first proposed, no one was worried about dark matter, at least to the first degree. And so the fact that you write the consistent mathematics and it automatically starts to provide candidates for dark matter, this is seems like it might be one of those serendipitous occurrences that we see occurring over and over in theoretical physics. So The question of my favorite, the LSP, because it will, we think, solve the dark matter problem.
All right, we have time for one more question. I see a student. Okay. Actually, no. Okay. As long as they're quick questions, and we'll do 3 quick questions. Okay. Well, why do you take? Okay. We'll see how it goes.
So this might reveal a hole in my understanding of the Standard Model, but is there a reason why there shouldn't be more than 3 generations of the particles? That seems like a nice symmetry.
It's a natural question. It's actually a very good question, and it's a question that particle theorists have thought about. What we can tell you is the following, that if you look at the Z particle, which is one of the things that I showed on my list, and you study it very carefully, what you find is that the patterns of decays that we see in the laboratory tell us that there are no more than 3 generations that are like the ones that we see. So there are no more than 3 generations of electron and its neutrino, muon and its neutrino, tau particle and its neutrino. The decay particles rule out more than 3. Now, that's an experimental observation. That's not a mathematical reason. So we don't have a mathematical reason for why there can't be more generations. And the other thing that it doesn't rule out is forms of matter that are not like the doublets of neutrinos and their associated charged particles. Maybe, in fact, people look for other more exotic things, Majorana particles, sterile neutrinos, all kinds of things that David knows more about than I do. And so, yeah, there's lots of room for asking that question, and people ask it all the time.
Okay, one more question from Phil Phillips, one of our speakers.
Okay, so since I finally got the microphone, I'll ask 3 questions.
Did you say 3?
Oh, no.
I'm sorry.
No, one last question.
You know, on an aircraft carrier, when the landing chief does this, so you get 1.
Okay, so I'll ask 1 question. What was actually found on July 4?
What was actually found is that's a very good question because it's not completely clear.
That's why I asked the question.
I know. It is not completely clear what was found on July 4th. And if you read very carefully the releases from CERN at the time, for those of you who are really good readers, you could detect a kind of ambiguity in the language that was very unusual for when particle physicists make an announcement of a discovery. So, was 1 particle or 2 particles discovered? We're not really sure. If you read very carefully, we don't know that this is actually the Higgs particle that we found. Was it 1 or 2 particles? And in fact, if 2 Higgses are found, people like me are going to just be hitting the roof because supersymmetry says you ought to expect more than 1 Higgs. Do we know that the spin is 0? Not completely. I have friends who work at the laboratory. I've talked over them. We're not sure. We know something is found. We're not sure if it's even the Higgs that our mathematics has predicted. That's part of the reason why the experiments are continuing past July 4th and will continue until the shutdown. The LHC is going to be shut down for most of next year for an upgrade, where data is still being continued. There is expected to be another announcement by the 2 groups in December, where hopefully this kind of ambiguous language that I talked to you about will be removed and we'll be able to say, aha, Peter Higgs deserves his Nobel Prize.
Thank you.